Continuing our journey in Chapter 12, we're going to move forward to rate laws and orders. And so there's our learning outcomes expectations. Feel free to pause so you can read through those before we dive into the content. All right, so previously we talked about chemical reaction rates and factors affecting reaction rates. We talked about change in concentration over change in time. And now we're going to introduce a more convenient representation or more information-dense representation of rates of reaction, and we're going to talk about rate laws. And so let's take a reaction right here, just as an example. We'll combine Br2 with formic acid to give you Br minus H plus and CO2. And the reason we're choosing this reaction is because this is a colored species and all these guys are colorless. And that makes it really convenient because it allows us to measure how this reaction progresses simply by color. And so while this reaction might start out red-brownish in color, as it progresses, it's turning Br2 and HCOOH into these guys here, which are colorless. And so you can actually see that over time. The color is disappearing. And so as it progresses, we can watch the disappearance of this Br2 species. And so the amplitude of the color or the intensity of the color is directly proportional to this concentration of Br2. And so we'd use an experiment like UV-Vis to actually monitor color over time. We could use Beer's law to figure out what the actual concentration is. And so you don't have to necessarily know that, but know that we can generate tables that look something like this, like we did previously. We have time here, and we have concentration of Br2 here, which is proportional to color. And so from this graph, just like we did from this data, just like we did last time, we can make a graph, right? On the y-axis, it's concentration of Br2. On the x-axis, we have time. And so you can see Br2 is disappearing over time, exactly what you'd expect from those previous photos, right? The color went away as the reaction progressed. And so we can take this and we can figure out the rate of reaction whenever we want. From our previous conversation, we said rate is equal to change in concentration over time. Br2 is going away. It's a -1. The stoichiometry on this reaction is 1. And so there's your rate expression, delta Br2 over delta T, negative sign there, final minus initial, time final minus time initial. And so we can do this math like we did previously anytime we want. And so we can do it here, we can do an instantaneous calculation here, and we get 2.96 times 10 to the minus 5 molarity per second. Here at this 200 second mark, it's 2.09. Here at the 300 second mark, it's 1.48. And so what you'll note here, and again, we talked about this previously, the rate changes with concentration, at least with this particular reaction. And so the rate progressively gets slower as the concentration of Br2 goes away. And so we have this proportionality. Rate is proportional to Br2. And so the problem is, if we want to report how fast this reaction is, it's not super helpful to report any of these numbers unless we have to add all these qualifiers, like when measured at 200 seconds after starting with this concentration, we get this number here. And so what we want is a more general way to describe the reaction where we don't have to say when we took it, but instead we have some descriptor of how fast it is that can be used at any of these time intervals. And so looking back at this data, we have a progression of time and a progression of Br2 concentration. And so we can measure the rate at every single point in this graph, right? We can do the instantaneous rate anytime we want. It's basically the instantaneous change, and we can get a rate associated with it. And so you'll notice time, as it progresses, Br2 goes away, and you can see the rate of the reaction slows down, which is what you'd expect based on that curve decaying gradually. And so we know that the rate is proportional to Br2 concentration. And what's interesting about this is for this particular reaction, if we graph Br2 concentration versus rate, our previous graph was time versus Br2 concentration. This time we're going to graph these two parameters. We're going to do rate and Br2 concentration. And something you'll notice is that this is a linear relationship. And we are always excited when we see linear relationships because we have a y equals mx plus b. It tells us the relationship between x and y is based on the slope and the intercept, which in this case is 0. And so what we have in this case is the x-axis is Br2, insert that there. The rate is the y-axis, so we insert that there. And we get an equation that looks like this. Rate is equal to the slope, which we're going to denote as k, times the concentration in Br2 plus 0 because the intercept is 0. And so if we look at this data, we get a constant number for k, right? It's the slope of this line, or it's a relationship between rate divided by concentration of Br2. And so if you do that math, we can find that this number is constant, 3.5, 3.5, 3.5 times 10 to the minus 3. And so what this is effectively the rate constant for the reaction. It tells you the proportionality or the relationship between BR2 and rate based on the slope of the line that's associated with this graph. And so this rate constant is really, really useful. It's a proportionality between concentration and rate. And what's nice about it is you can see that this is a constant number. It's a rate constant. It is a constant. Unlike the rate, which changes as the reaction progresses, the rate constant stays the same. And so it tells you that, the rate changes, the BR2 changes, but this K will always be the same number at a given temperature. And so it's this universal descriptor of this particular reaction where you don't have to describe what concentration you started with or what time interval you chose. Instead, this rate constant is always constant for this reaction at a given temperature. And so what that relationship is effectively the rate law. Rate is equal to the rate constant times the concentration of BR2. This describes the relationship between concentration and rate, and it's all dictated by this rate constant K. And so, again, that's what a rate law is. And so the generalized form of a rate law is the relationship of rate of reaction to the rate constant and the concentrations of reactant raised to some powers. And so here we had it's a first order reaction. Basically, there's a 1 exponent on this BR2, but it doesn't necessarily have to be 1. Concentration can matter more, concentration can matter less. And so the generalized form of the rate law is this equation down here. We have A plus B going to products. We can write a general rate law for this reaction that is rate is equal to K, which is basically that slope of the line, that rate constant, times concentration to the A to the X and B to the Y, where these exponents can change depending on the nature of this reaction. And so yeah, there's your generalized form of the rate law. And so a couple things to note about this. Rate laws are always defined based on the concentration of reactants. I mean, there is a scenario where you could do it based on products, but the formalism in the community is you want to define rate laws based on the reactants. The other thing to note is there's X and Y here. And so for the BR2 reaction, that was just 1, and it's known as a first order of reaction. And so what this X and Y does is it's the order of the reaction. It basically tells you how much these A's and B's matter. And so something really important to note, and it's easy to confuse this, is these X and Y's are not dictated by the stoichiometry here. That's not what these X and Y's are describing. It's telling you something very specific about how the reaction happens, not just the stoichiometry of things that you put together. And so those are the order of the reaction. And so the hard part about this is that for rate laws, X and Y have to be determined experimentally. It's not something you can just, look at the formula and determine what X and Y are. You have to learn something about the actual reaction as it progresses. And so again, you have these X and Y's. These are known as the reaction order. It's basically it tells you how much the concentration of A and B matter for reaction. And so if that number is 0, it doesn't matter at all. If that number is 1, it matters a little bit. If that number is 4, it matters a lot. And so it tells you how much A happens or how much A matters in the reaction. And so the language we use to describe this is we can say the reaction is Xth order in A. And so if this is 2, it's second order in A. If it's 1, it's first order. If it's 0, it's 0 order. If it's 3, it's third order. Same thing with B. It's Yth order in B. So this is 2, it's second order in B. And so you can have a reaction that's first order in A and second order in B, 0 order in A, third order in B. It depends on what these X and Y coefficients are. We also have a term called overall order of the reaction. We basically say, okay, sum these exponents together, and that tells you the overall order. And so if it's first order in A, second order in B, it is third order overall because it's 3 things that matter in this reaction. 1 of these and 2 of these guys. And so this doesn't change the reaction. This just is a convenient way for us to discuss what is the order of the reaction. It gives us a really simple way. If I tell someone it's a second order reaction, they already know either it's 2 A's or 1A and 1B, so on and so forth. It tells you about the species that are reacting. One thing to note is if a reagent is 0 order, it's not included in the rate laws. And so typically if we do experiments and we find out Y is equal to 0, B to the 0 is 1. That's just the way math works. And so we just leave B off entirely and we would say rate is equal to K times the concentration of A to the X, whatever that X is, and just ignore B entirely. And so what's important about this, remember, it doesn't have to do, this X and Y has nothing to do with the stoichiometry. It's not the where you started and where you ended. It tells you something about how the reaction progresses, which is the reaction mechanism. It tells you basically what molecules are involved in the rate limiting step and how many of each molecules are needed during that particular step. And so, again, it's not related to the stoichiometry. It's dictated by how the reaction progresses. And so here's just a quick example to emphasize that point. F2 plus 2 ClO2s gives you 2 FClO2s. And so you're combining fluorine with ClO2 and generating 2 of these species here. So you break a FF bond, you form an FClO2 bond, FClO2 bond to generate this guy right here. And so if you do the experiment and you figure out the rate law and you find out the exponents on these, you have K times F2 to the 1, ClO2 times to the 1. And so you'll note, stoichiometry has nothing to do with this rate law, right? From experiment, we determine this. This is just what happens before and after the reaction. And so we simplify this because this number is 1. We don't actually draw the 1 usually. It's just assumed to be 1 if you don't leave the 1, because that's again, how math works. But what this tells you about the reaction is, while it takes, stoichiometrically, it takes 1 of these to react with every 2 of these, the rate of the reaction is essentially limited by an F2 interacting with a ClO2. Why? Because there's 1 of these and 1 of these, and that's what dictates the reaction. If this was 2, it would tell you you need 2 of these and 1 of these during the slow step of the reaction. And so while overall stoichiometry, you need all these to interact, the thing that dictates the rate is simply this going with this, and eventually whatever that makes will react with another ClO2 to make you product. But at the rate determining step, or what dictates the rate, is 1 of these interacting with 1 of these. And so again, this is why reaction order must be determined experimentally. Nothing about the stoichiometry tells you what step is actually slowing down your reaction. And so that slow step tells you how these interact. And we'll get into more detail on this when we talk about mechanism. But again, I'll hammer home the point. This A and B does not dictate the rate law. The rate law is dictated by the nature of the reaction, and it must be determined experimentally. And so how do we actually determine those X and Y's? And so here's that reaction again. What you're essentially going to do is you're going to get a data set. You're going to vary the concentration of these species, measure the rate of the reaction with that concentration, at least the initial rate, and then you're going to get a graph that looks like this. So you say, okay, I had a concentration of F2, 0.1, I had a concentration of ClO2, 0.01, and I got an initial rate. That's that basically instantaneous rate at the start of the reaction. I got 1.2 times 10 to the minus 3. I kept F2 the same, I changed ClO2, I got a new rate. I doubled F2, I kept ClO2 the same as the initial reaction, and I got a rate that looks like this. And so it's saying I varied this concentration, and got an initial rate for the reaction. And so we know the rate law has to look something like this. Rate is equal to K, F2 to the X, ClO2 to the Y. What we don't know is what X and Y are. It could be 0 for both, it could be 1, it could be 2 and 1. We have to figure that out from this data set here. And so we can do this by 2 different methods. One, the algebraic way, and another one is by inspection. And so for the most part in general chemistry too, these numbers will be pretty straightforward. They'll be multiples of 2 and so on and so forth. But it can get very, very complex. And so for the most part, inspection works for a lot of reactions. And so what we can do is compare reaction 1 and reaction 2, right? And we can see, okay, F2 stayed the same, Cl2 we multiplied by 4. And so if we keep this constant, essentially the only thing that's making the rate change, as in making this number change, is this change in concentration here. And so we took F2, we kept it constant. ClO2, we saw that it changed by a factor of 4, or it quadruples. And guess what? We can see the initial rate changes by a factor of 4. And so it basically says that any concentration change you have to Cl2, it changes the rate proportionally. And so what does that mean? It means Y has to be 1, right? And so there's the proportionality here. Here's an exponent Y. That Y has to be 1 for these two to be proportional. If it's 2 here, then any change here should result in an exponential increase in rate. And so if this was concentration is 2, this number is 2, you should see a 4-fold. If you change this by 4 and that's a 2, you'll see the change by 16. And that's not what we saw. We saw a change of 4 giving us a change of 4. Those are proportional, and Y has to be 1. And so we can do the same thing to figure out how much F2 matters. And so we do that by keeping ClO2 constant, which will compare reaction 1 and 3, 0.01, 0.01, ClO2, we don't care what happens to that. We're only looking at what happens when we double the concentration of F2. And then we look over here at our initial rate, and we have doubled the rate of the reaction. So if ClO2 is held constant, F2 doubles, the rate doubles, that has the same relationship. The exponent on F2 has to be 1. Now, if we double the concentration of F2 and the rate quadruples, as in this is 4 and this is doubled, that means the exponent has to be 2. But in this case, we didn't see that. We saw F2 doubles, rate doubles, there's a proportionality, X is 1. And so we get a rate law that looks like this. Rate is equal to K times the concentration F2 to the 1, ClO2 to the 1. We simplify this, get rid of the 1s. That's your rate law right there. And so we fixed one concentration, saw how the other concentration affected rate, and then vice versa, and we figured out the exponents of X and Y, and we got a rate law that looks like that. And so if we have a rate law, we can actually do the math directly and calculate the rate constant. We can choose any one of these experiments. We can choose this data, we can choose this data, or this data. We can't mix and match, but we can choose any of them. We simply plug in concentration of F2, concentration of ClO2, and we have rate. And so that's the parameters we have for this reaction right here. Plug in, I apologize, this should be 0.01, but you get the idea. You plug these concentration numbers in here, you know the rate that goes on this side, you solve for K, and you get a number associated with that. And then so again, you can use any of these experiments. We use the data to figure out the exponents, then we use the overall formula, the rate law of the reaction, to figure out the rate constant for the reaction. And so our steps are, we measured the impact of concentration over time, we found a rate law, and we calculated a rate constant for a given reaction. And so that was by inspection. We basically looked at the proportionality and said, this changed by 4, this changed by 4. And that works really nice when you have nice round numbers and they change by factors of 2 or factors of 4 or don't change at all. But you can also have ones that are much more messy and complex. And so here's an example of a reaction. We changed the concentration. We changed the initial rate based on the changes in those concentration. We have a generic rate law. Rate is equal to KNO2 to the X, H2 to the Y. And now we need to figure out the rate laws for these numbers that are a little more complex than the ones we did previously. And so one way to do this is set up the algebra. You basically take two experiments, experiment 1 and experiment 2, and you set up a proportionality. You basically say, you know, this rate constant K should always be the same no matter what. So if I can cancel out K's and I can cancel out one of these concentrations, one of these variables, I can isolate the variable X here. And so that's what this proportionality is effectively doing. And so we pick a condition where H2 is held constant, those guys cancel out, K's cancel out. All of a sudden we have this relationship between the rate, measured rate, and then the concentration to the exponent. And so essentially you can go through and solve this math. And so again, 10 divided by 5 is 2, even if it's 10 to the minus 3. 5 divided by 1.3 is approximately 4. We have 4 is equal to 2 the X. We solve for that, X has to equal 2. And so we can do the same thing with reaction 2 and 3. We keep this constant, this doubles. We can see this doubles by inspection. I'd tell you y is equal to 1. Or you can set up the algebra and you can say, okay, we kept this constant, that cancels out, K cancels out. We have this ratio to the y. Do your math, 2 equals 2 to the y is equal to 1. And so this is the more formalized way to do it. And again, if these exponents end up being like 0.5 or they're 1.5 or -1, this is kind of how you have to do that math. It's really hard to do by inspection alone, but if the numbers are nice and round, you can do the inspection process. So something to note about this rate constant, right? Rate constant is an intrinsic descriptor of the reaction. It tells you the relationship between the concentration of species and the rate through this rate law expression. So something to note about this rate constant is the units on rate constant actually change. And the reason is because they have to. And so rate, remember we defined at the start, that's always molarity per second. Concentration is all molarity. And so the relationship between this part of the equation units and this part of the equation units is going to be dictated by this M and N. And basically the units on the rate constant have to cancel out with these two m's to the exponents, so we get molarity per second. And so what does that mean? So this is always molarity per second. This is going to be molarity to some exponent per second. In this case, molarity m, molarity n. These, whatever these exponents here are going to dictate what this exponent here has to be. And so basically you need all the m's to cancel out on this side so that you get molarity per second on this side. And so it turns out if you do the algebra, the m here and the n here, m plus n minus 1, the negative sign of that gives you this value x. And so it might be easier to conceptualize this way. This is the formalism, the equation behind it. But here we have rate laws, right? We have rate is equal to k, rate is equal to k to the 1, rate is equal to k to the 2, or rate is equal to k to a times b, zero order, first order, second order, third order reaction. The units on k change, and it's because they have to. If this rate is always molarity per second, the units on k here have to be molarities per second. The units of k on here have to be per second, because per second times molarity gives you molarity per second. In this case, you have molarity squared, and so here you have to have a molarity on the bottom of k to cancel that out. And so it's the units on k in this case is 1 over molarity second, so molarity can cancel with one of these, so it's overall molarity per second. And so go through and do the algebra. One of the big take-homes on this is that this k, even if you just have the number and the units, it tells you something about the reaction, right? And so if the units on k are molarity per second, it tells you a zero-order reaction. It tells you the concentration doesn't matter. If it's the units on k are seconds minus 1, it tells you it's a first order reaction. It doesn't tell you what it's first order with respect to. It could be A or B. It tells you the overall order is first order. Likewise, if it's molarity minus 1, second minus 1, it is, it's a second order reaction. And so note, you could have units for a 13th order reaction, right? And this algebra still stays exactly the same. It tells you what the order of that reaction is. All right, so to summarize, we talked previously about this rate expression, the proportionality between the change in A and change in B and so on and so forth. And today we introduced this idea of rate law. And so the rate expression basically tells you how much these things are going to be consumed versus how fast these will be generated. You can create this from the equation. It's based on the stoichiometry. It's describing the change with reactants and products. And the rate changes as the reaction progresses, or at least with many reactions it does. Now, from this, we figured out a rate law, right? We figured out the proportionality between concentration reactants and the rate of the reaction is going to be dictated by this rate constant here. And so this is something we have to determine experimentally, whereas rate expression is just the stoichiometry. This rate constant is an intrinsic descriptor of the reaction. It doesn't change as the reaction progresses. The rate constant is always constant, and it tells you the relationship between rate and concentration. And unlike rate expression, this is only expressed in terms of reactants. And so again, this tells you the relationship, how these variables change relative to each other based on stoichiometry. This one gives you an intrinsic descriptor, which is the rate constant, and it tells you the proportionality between rate and concentration. So yeah, there's our summary. We can't just use reaction rates to describe a reaction because those reaction rates can change. Instead, we figure out something called a rate law. It's a relationship between concentration and rate of the reaction, and the relationship between those two is dictated by the rate constant K of the reaction. And so we also figured out there's orders to the exponents on the concentration. That's the order of the reaction. We have orders for individual components. We have orders for overall reaction, and we must determine those experimentally. We take the initial rates and changes in concentration. We can do inspection or algebra to figure that out. And that gives us the rate law of the reaction. Also, we have K, which has different units on it depending on what the order reaction is, and it's because it has to. All right, so that closes out our rate laws. In the next presentation, we'll start diving into integrated rate laws.